This is Math 30-2 once again, and we are in the chapter looking at logarithms. And we're on to our second lesson, 7.2, where we will evaluate logarithmic expressions. So as you can see here, looking at the measures of success, by the end of today's lesson, we want to be able to write a logarithmic equation as an exponential equation and vice versa. So we want to be able to switch back and forth. And then without using technology, we want to understand logarithms well enough that we can evaluate them when they're equal to whole numbers. To begin with, I would like you to determine the value of each exponent to the nearest tenth. So here, what is this y value equal to? Here, what is that y value equal to? Give it a shot. See what you come up with. You can pause the video now to do those questions. Well, here you can see my answer for question number 1. So what I did to begin with was I said, well, let's let this left side, 81, be one equation. So I said y equals 81. And then the right side be another equation, y equals 10 to the x. So notice I've changed this y value to an x value because that's what I need to do on my calculator if I'm going to graph it. So when I'm looking at the intersection point on the graph here, I'm actually looking for this x coordinate, and that's the solution that I'm going to call my y value. And again, it's because I replaced this y with an x when I entered the equation. But we get that intersection point at y equals 1.9. So it'll be a similar process for number 2. Remember that e is Euler's constant. So if you just use the e to the x button on your calculator, or here as I did on Desmos, it will actually put in that irrational constant, which is 2.718 and so on, approximately. So again, you'll notice that where I had my y up here, I replaced it with an x in this equation, so I'm looking for the x coordinate of this intersection point, and I get 3.2. So hopefully that was fairly straightforward to you. Today, we want to look a little further at the relationship between exponential functions and logarithmic functions. So first of all, a review from what we looked at in the previous lesson. If I have this expression, the log of x equals y, and there's no subscript here, then we assume that there's a subscript here, which is a 10. So we'd say this is a log base 10 of x equals y. Not very easy to read 10, but that's what that's supposed to be there. That's a little bit easier to read. And then if you remember from yesterday, what this is saying is, if I was to take this x and rewrite it as a power base 10, so I'm going to take x and I'm going to rewrite it. So here's my x, I'm going to rewrite it as a power where the base is 10. This is telling me that y would be the exponent. As we look at the next one, remember yesterday this ln, this is a logarithm, and we said that this is the same as the log base e of x. So this is saying if I was to rewrite x, so I take x, I'm going to rewrite it as something equivalent. Log base e of x says I'm going to rewrite it as a power where the base is e. Then the exponent will be a y. So what's written here in logarithmic form is exactly the same as what's written here in exponential form. Both of these equations are saying exactly the same thing. The advantage of one over the other is here I have my y variable in the exponent. That's not great. Here I have my y value isolated. That's how we prefer to see it, particularly when we're going to look at a graph. So these two are saying the same thing. And in the same way, what we have there with the natural logarithms, so when we have a log base e, it's called a natural logarithm. Those two statements are saying exactly the same thing as well. If y equals log base b of x, that means x equals e to the y. Identical statements written in different ways. So in a more general form, log base b of x equals y says, if I'm going to rewrite x, so I'm starting with x, and I'm going to rewrite it as a power, this little subscript here tells me the base. The base is b. This logarithm is an exponent, so the y goes in the exponent. So is this something I can drag out? Let's see. If x is written as a power with b as the base, then the exponent will be y. Just like I said as I was writing it out. So as we look at question 3 and 4, we can see they are exactly the same as questions 1 and 2. So we want to rewrite these in logarithmic form. So now we want to go backwards. If I have an exponential form like this, how do I work backwards to be the logarithm? So let's go backwards here. Y is the exponent. Y is a logarithm. So y is equal to the logarithm. The base in the exponent, or the power I should say, is the same as the base in the logarithm. Notice here that this is subscripted, so it's down lower. It's not on the same line as the logarithm there. Maybe I'll just put a line in here to help me be clear with that. So suppose I have a line there. That 10 is a subscript. And a logarithm operates on the power. Well, 10 to the y is the power, but 10 to the y is equal to 81. So we'd say the log base 10 of 81 is equal to y. There's the base. The exponent is what the logarithm is equal to, and it operates on this power. We're imagining 81 to be a power base 10. So this is something that we could evaluate in our calculator. So pull out your calculator and you'll find a log button. It may not ask you for a base, but if it does, you can put in a base 10. Just find what is the log base 10 of 81. So here I have a calculator up, the log of 81, hit enter, 1.9 is what it rounds to. Well, that should look familiar. That was our answer in question 1 as well. So this is just equal to, well, approximately equal to 1.9. And we could guess that it's going to be similar for the next one as well. But let's go through the process. I want to rewrite this as a logarithm. Remember, a logarithm is an exponent. So y is equal to the log. The base is e, same as the base in my power, and it operates on that 25. Now, when you're going to put this on your calculator is programmed to work in log base e as well, but there's a short form which is ln. So ln of 25, that's what we want to put on our calculator. So there I have it, the natural logarithm of 25. Oh, it already gives me the answer before I hit enter even. There you go, 3.2. And as we scroll up here, 3.2 is what we had in question number 2 as well. So we're getting exactly the same value. So using that information, I'd like you to try these check your understanding questions. Can you rewrite these two powers as logarithms? Pause the video here, try these two questions. Then you can restart the video. Well, a logarithm is an exponent. This time, let me start with a logarithm. So I'll write the log. What base do I get? I look at my power. The base is a 5, so my base here is a 5. My logarithm operates on that x to give me the exponent, which is y. This time we're not evaluating, we're just rewriting it in logarithmic form. Similar idea for the next one. I have the log. That's a funny looking log. Looks like joy. Joy to the world. Christmas time. Okay, the base is 2/3. Often when we have a fraction in the base, we'll put this in brackets down here. It doesn't have to be, but it can help us clarify. And the logarithm is an exponent, so the y is over there. The only thing left over is the x here. Now in the previous question, I put brackets around the x. That's good for clarity, but we don't have to. We could write it like this. This one over here, we could have just written as log base 5 of x equals y. Be careful. This 5 in the x, it's not a base and an exponent in a power. That's not how they work. This is the base for this logarithm, and this log base 5 is operating on this. It's kind of like if I did the fifth root of x. This 5 is part of this radical function, and I need that to describe the index in order to know what type of radical this is. It's not a square root, not a cube root, it's a fifth root. Same thing here. This 5 is critical as a descriptor of this logarithm. It's not part of this x at all. Okay, so it's a log base 5 operating on the x. Well, then let's work in the other direction. Suppose I have a logarithm. Well, I know in my logarithm, my base is a 3. So let's start with the base. I also know the logarithm is an exponent, so the y goes in the exponent. This is equal to what the logarithm was operating on, the x. Let me put it in different words. Remember that we said earlier, if I have log base 3 of x, it says if I was to take x and rewrite it, so there's the equal sign, as a power where the base was 3, there's my base of 3, the exponent would be y, and that's why I get the y in the exponent. Let me use those words as we look at number 8. This is saying if I was to rewrite x as a power where the base is 0.5, the logarithm tells me what the exponent would equal. So the exponent is a y. Let's try a couple more. We want to evaluate these without using technology. We could plug it into our calculator, but we should be able to do without a calculator as well. Remember, if there's no base written here, there's an invisible base of 10. That's the common logarithm. So what I want to do, remember a logarithm says if I was to rewrite 100 as a power base 10, well, I can do that already, right? Because, and I'm going to write the base in this time just to make it easier. If you leave it out, that's okay. 100 is the same as 10 squared. The logarithm says if I was to rewrite this number as a power base 10, the logarithm tells me the exponent. What's the exponent? A 2. Let me think of this in a slightly different way, more similar to what we just did. Suppose I said this is equal to x. Let's rewrite this in exponential form. The logarithm says if I was to rewrite 100 as a power where the base is 10, the logarithm tells me the exponent is x. Oh, 10 to the x, 100 is 10 squared. So x equals 2. So this is going back to those ideas we previously looked at in the chapter on exponential equations and functions, where we can rewrite both sides as powers of the same base. So we're getting to the same endpoint. This is more familiar, so you may want to work through this way, but I would challenge you to push yourself to think like this. How do I rework this? And so I'm rewriting that 100 as a power with a base of 10. The exponent that I get up here is my answer. It's the value of that logarithm. Why don't you try number 10? Pause the video and restart when you're ready. Well, I'm going to do this the first way again. If I was to rewrite 1,000 as a power base 10, then what would the exponent be? Quick correction there, I do want to rewrite this logarithm where I write that 1,000 as a power base 10. And then as long as this base and that base are the same, the logarithm gives me the value of the exponent. There are two more check your understanding questions here for you to try. So pause and restart the video once you're done those. There's number 11. Remember here that ln is a log base e. So we already have the same base here and the same base there. So this logarithm just tells me the exponent, which is a 4. Let's look at a couple more here. We want to evaluate each logarithmic expression without using technology. With these questions, I'm going to demonstrate how we can do them in two different ways. You will probably find one way that you like more, but I'd really encourage you to work at getting comfortable with the second way as well. So I'm going to start with a way that is generally less comfortable. And that would be to rewrite this and say, well, log base 2 of 64. So this is saying, if I was to rewrite 64 as a power with a base of 2, so that's what I'm going to do. I'm going to keep the log base 2, but I'm going to rewrite 64 as 2 to an exponent. So I may need to do some guessing and checking, get out the calculator, find what's 2 to the 5th, 32. Oh, 2 to the 6th, that's 64. So this is a 2 to the 6th. And now that I have log base 2 of 2 to an exponent, this is just equal to the exponent. So that's what that logarithm evaluates to equal. Let me do number 14 in the other way. The other way would be to say, to turn this into an equation. And I could use whatever variable. I'm just going to pick x. You could pick y, l, whatever you want. And then rewrite this in exponential form. Well, the base is 2. A logarithm is an exponent, so the exponent is x. And this is equal to 1 over 64, the power that the logarithm was operating on. And then we solve it like we solved equations like this in chapter 6. So I'll rewrite that. So I'll have 2 to the x is equal to 1 over 2 to the 6, because again, over here I already found that 2 to the 6 was equal to 64. And then I can rewrite that right side. 2 to the x is equal to 2 to the negative 6. Oh, power equals power, base equals base, exponent equals exponent. So that's the other way we can do these types of questions. Let me go back to the first way for number 15. The first method would say, if I was to rewrite 0.5 as a power base 2, what would the exponent be? Well, let's see, what can we do? This is log base 2 of, well, 0.5 as a fraction is 1/2. That's not quite a power base 2 yet. 1/2 is the same as 2 to the negative 1. Okay, so I've rewritten 0.5 as a power where the base is 2, so my logarithm is equal to this exponent, negative 1. Number 16, I'll do the second method again. So I'm going to set this equal to x. So this says, if I were to rewrite in exponential form, my base is a 2. A logarithm is an exponent, so the exponent is x, and this equals 1. Ooh, well, this is a tricky one, but remember, 1 can be written as a power with any base. So I'm going to choose the base of 2 as long as my exponent is a 0. Remember, anything to the exponent 0 is equal to 1. Power equals power, base equals base, exponent equals exponent. If I thought this one through using the other method, what I would have done is I would have said, well, log base 2, how do I rewrite 1 as a power base 2? Oh, that's 2 to the 0. And that just equals the exponent. There you have the first part of this lesson. So some practice questions for you to work through, and then you can continue on to the next part of this lesson.